Do you want to perform proof of concept experiments in vivo that a given mechanism of action can actually impact disease symptoms? Or you want to explore the in vivo potency of your optimized drug candidates with a complex mechanism of action, such as immunomodulators? Then beware of the six following common errors during in vivo experimentation. Error number 1. Forget to establish the PK of the drug prior to testing its in vivo efficacy. Study design is everything in vivo experimentation. If you don't know upfront the PK of the drug you're going to test, how will you select the right dose or the right dosing frequency? How will you know that its concentration in the target tissues is high enough to be able to observe potentially an efficacy? It is also possible that beyond the parent drug, you also have active metabolites. If that is the case, it is also important that you know their PK behavior. An advice: when establishing the PK of a drug for the first time, do not sample only plasma, but also sample all tissues, even beyond the tissues you think are the target tissues. Even if they are not of immediate interest, you can save them for later analysis if required. Error number 2. Forget to measure the PK of the drug you're analyzing while testing its in vivo efficacy.
If you do not measure PK while testing for drug efficacy, how will you establish PK-PD relationship? And how will you compare between drugs? It might very well be that one drug works much less well than another in terms of efficacy, and that this is entirely explained by its PK profile. Also, how will you explain unexpected outcomes? Let's assume you were hoping to see efficacy and you don't. Maybe it is because of, again, PK exposure. One important point here, again, is to sample all tissues, even if they are not of immediate interest. Please save them for later and analyze them if required. That will avoid that you have to repeat the entire experiment just because you missed one tissue. Another important point: do establish the PK and the PD in the same animal. It's always a mess if you separate, on one hand, PK in one group and on the other hand, PD in another, even in rodents like mice.
Error number 3. This one is for antivirals. Focus only on viral load as parameters of efficacy. First, it is essential to select the right animal model. The whole goal is to translate as best as possible to humans. And it might very well be that clinical observations allow a better translation than viral load to humans. So think, for instance, of body weight, body temperature, respiration pattern, position and pain, humane endpoints, interaction with cage mates, or activity. In my experience, reduction in body weight and especially activity are one of the most sensitive ways to know if a mouse is not in an optimal condition. I show here on the right an example of a mouse placed in a new environment or at night during its active time in a cage with cameras. You can then measure the distance that is being run by the mouse. This is a very sensitive parameter to know if the mouse is doing right or not. Error number 4. Don't train thoroughly for injection and sampling techniques. This one should not happen. I've unfortunately seen it a few times. Improper injection techniques can lead to misdosed animals, especially for IV, PO, or sub-Q, or even IP, while improper sampling techniques can lead to insufficient blood samples. So here, the key is to train, train, and train again on a daily basis prior to the experiment start till you really master the technique. Error number 5. Fall into the many statistical and blinding biases. If you're not a biostatistician yourself, I strongly encourage you to perform power analysis with a trained statisticians. There are just too many ways to make mistakes here. If you don't have a statistician in your lab, just ask the local ethical committee. They may be able to help you. Next, randomize animals into the different cages. The randomization should be done after acclimation. So upon animal arrival, acclimate, then randomize, then acclimate again to the new cages, and then start the experiment. The randomization should be performed per age, sex, litter, body weight, and if you're performing a virology experiment, per viral parameter. So for instance, for HBV, the HBs antigen plasma levels can define the antiviral outcome and thus are an important parameter to consider during the initial randomization. Also use ear or back marks, or if you can, individual microchips to identify each individual animal. Next, spread the experimental groups over the different animals in the cages. Don't use C. So in the example on the right, there are 4 animals receiving 3 different treatments: the black, the white, and the yellow. In the randomized to treatment group design, the animals in the first cage are all receiving the black treatment. The animals in the second cage are all receiving the white treatment, and the animals in the third cage are all receiving the yellow treatment. There might be a huge cage bias on the results. Instead, try as much as possible to use A, the completely random design, where each treatment is randomly assigned to each animal independently of the cage. If that is not possible, another option is to use B, the randomized block design. There, in each cage, in that case there would be 4, you can find 1 animal receiving each of the different treatment groups. If you then use that design, you can perform a double ANOVA for the treatment effect and for the cage. In Excel, you can easily use a random numbers generator to more easily allocate treatment and cages over the different animals. Next, implement blinding of experimental groups allocation. What I mean here is that the first operator, using a random number generator, assigns whether the black, white, or yellow correspond to vehicle treatment 1 or treatment 2, and independently, a second operator actually injects and administers the treatment, so black, white, or yellow, to the animals. Now coming to the last error, error number 6. Include only one reference compound or with only one mechanism of action. The easiest here is to give you examples. So the first example is for RSV, so respiratory syncytial virus cotton rat model. This is a very widespread model for RSV. And here it is important to include one small molecule inhibitor, a large molecule inhibitor, and also, for instance, interferon alpha as reference compounds, as these might have very different impacts on the virus. They will allow you to better evaluate the effect of your own antiviral. A second example is with toll-like receptor agonists. So here, do use on one hand one small molecule, but also one natural ligand, as these two may behave very differently. In summary, do establish PK in plasma and tissues prior to testing in vivo efficacy of a drug. Do measure PK in plasma and tissues while testing the in vivo efficacy of a drug. Do not focus only on viral loads. Train enough and thoroughly for injection and sampling techniques. Don't fall into the many statistical and blinding biases. Do get the help of a biostatistician if need be. And include multiple reference drugs spanning multiple mechanisms of action. And you, do you have any other advice or error that you would like to share? Leave a comment.